Welcome back, everyone. Today we're diving into one of the most fascinating topics in science, electrons. We're going to explore how these tiny particles shape everything around us, moving step by step through the history of atomic theory. Our journey begins with Niels Bohr, the first scientist to propose a truly structured plan for the atom's interior. Bohr imagined electrons zooming around the nucleus, much like planets zoom around the sun. He called these distinct paths orbits. Just like a planet's path, an electron's orbit is its specific track through space. But Bohr went further. He realized these orbits weren't just paths, they were actually specific energy levels. Each level has a unique size and energy. The smaller the level, the lower the energy it contains. Crucially, these levels are at fixed distances from the nucleus. There's no in-between for an electron here. To move to a higher level, an electron must gain energy. Think of it like climbing a ladder. You're either on one rung or the next. When it moves from a higher level back to a lower one, it releases that energy, emitting a particle of light called a photon. This process is what creates the light we see in everything from neon signs to the stars in the night sky. Let's look at a real-world example, the element calcium. It has a complex system of 20 protons and neutrons. In the Bohr model of calcium, we see these electrons organized into specific shells, starting from the center and moving outward. The first few shells are filled first, and the rest occupy the outer layers as we move further from the nucleus. The electrons in that very last outermost energy level have a special name. We call them valence electrons. These valence electrons are the stars of chemistry. They determine how an atom interacts and bonds with others. Now, as elegant as Bohr's model was, scientists eventually realized it wasn't the whole story. It was just the beginning. It turns out that energy levels aren't perfectly fixed tracks. Electrons are far more mysterious than planets. The big question that stumped the greatest minds was, is an electron a particle or is it a wave? Louis de Broglie proposed a revolutionary idea. He said that electrons are actually both. This is known as wave-particle duality. Waves can behave like particles, and particles can behave like waves. Then came Werner Heisenberg, who added another layer of complexity with his uncertainty principle. Heisenberg stated that it's impossible to know both the position and the momentum of a particle at the same time. If you know exactly where it is, you can't know where it's going. If you know how fast it's moving, you can't know its exact spot. This meant Bohr's orbits were gone. Instead of paths, we have an area of space where the electron is likely to be. We call this a probability cloud. It's not about where the electron is, but where it might be found. Finally, Erwin Schrödinger pulled all these theories together into one master equation, the Schrödinger equation. This equation became the foundation for quantum mechanics, the science of the very, very small. It uses both wave and particle behavior in the same calculation. It's a mathematical masterpiece. The formula gives us the probability of where an electron can be found at any given time, represented by the intensity of light. These energy states and wave functions are described by a specific set of what we call quantum numbers. So, let's recap the big ideas we've covered in this deep dive into electrons. First, electrons are in constant motion within an atom. They never sit still. Second, they always head for the lowest energy level first, filling up the shells from the inside out. And finally, those electrons in the outermost level are your valence electrons, the keys to chemical reactions. Quantum mechanics might seem strange, but it's the rulebook for how our entire universe works at its core. Understanding these tiny particles is the first step to unlocking the secrets of chemistry and physics. Let's go a bit deeper into those shells. Each one can only hold a certain number of electrons before it's full. The first shell is cozy, with room for only 2. The second expands to 8, creating a beautiful geometric balance. When these shells are full, atoms become incredibly stable. This is why some elements are so unreactive. But add some heat or electricity, and you can kick those electrons into high gear, jumping them to those outer levels. This excited state is temporary. They always want to return home to the lowest energy state possible. That return journey is what gives each element its unique light signature, its own atomic fingerprint. Back in the quantum world, these waves can interfere with each other, creating the complex shapes of orbitals we see today. These aren't circles anymore. They are beautiful 3D shapes, spheres, dumbbells, and clover leaves where electrons reside. It's a world of probability and beauty, hidden right before our eyes in every single atom of your body. I hope this step-by-step breakdown helped you master electrons. Science is a journey, and you're doing great. If you found this helpful, please hit those like and follow buttons. Subscribe for more deep dives into the world of science. Join our community of learners. This is Learn with Adeesha, and I'll see you in the next chapter. Keep exploring, keep questioning, and keep learning. See you next time.